Helo, a croeso I Carlan Cymru revision sessions. This session will be focusing on electronics. Okay, my name is Jonathan Williams and I teach electronics at the ysgol Maes y Gwendraeth. This is rhan 7. This is part 7 of our series in electronics covering AS and A-level. Today's lesson or revision series will be concentrating on filters and thyristors. Now these are topics which primarily appear in the A-level section, so the year 13 bits, okay, which will be examined in the EDUCAS papers in the year 13 exams. The session will last for around about 45 minutes, and if there's any questions, if you want to type the questions in on the question and answer section, I'll try and get back to them, either answer them for the next lesson, next series of electronics programs. This session is recorded, and the recording and any relevant resources of PowerPoint and mark schemes will be loaded up onto the e-sgol website. If you go onto the Carlan Cymru e-sgol website, just Google e-sgol Cymru, it'll come up with basically a menu, and if you click on the Carlan Cymru and the recordings, you'll get access basically to all the previous ones which have been done. There's access as well to other subjects in A-levels. You can have access to those from this series and from last year as well. Moving on to the electronics, as I've said in previous sessions, first thing that you need to be aware of, there are equations which are not in the data sheet, and you need to remember the most important one being the VIR. Okay, please make sure you write that down at the start of the exam paper, and that you are able to rearrange it so that you've got the V equals IR, I equals V over R, R equals V over I. The power equations are useful, as is basically the potential divider equation. Please remember those are not available in the data sheets. With the equations that we're going to be looking at today and using in filters and in Thyristor. First of all, you've got the XC. Okay, X stands for reactance. Adweithedd yw hwnna yn Gymraeg. XC cael ei mesur mewn ohms. Okay, measured in ohms. You've got the XC is for the capacitor and the XL is for the inductor. The Z will give you access to work out the impedance, again measured in ohms, for anything we have resistors, capacitors, inductors working together. Okay, please remember they're measured in ohms. You've also got your F0, which is 1 over 2 pi root LC. That is your resonance equation, which is used in filters. Thing to remember about resonance filters, at resonance, your current is basically a maximum value. That is really important. And at resonance, the capacitor and the inductor reactances are equal to each other. You've got dynamic resistance. So if you're playing around with filters, which use capacitors, inductors, and resistors, okay, that RD basically will let you work out the equivalent resistance, makes things easier. You've also got a Q factor. So with a Q factor, you've basically got a value to do with filters. You can have a sharp Q factor, which is good selectivity, sensitivity, and bad selectivity. Okay, and you can have a low Q factor as well. All right, so we'll be looking at those today. What we've got as well when it comes to thyristors, we'll be looking at phase angles. Okay, you've got the break frequency one as well, going back to the filters just for 1 minute. So you've got the break frequency for an ideal filter. Break frequency happens at a certain point there. Okay, use that one. I'll go back to the thyristor one. Okay, you've got the phase angle. Tricky one to use on a calculator. Okay, if you are watching the recordings, have a good little practice of putting that into your calculator by using the shift tan button. Okay, so what I've got there, showing a phase difference against supply voltages and capacitor voltages. Okay, so I'll be coming and having a look at through those. Okay, when we've got these things that you have to remember with filters, first of all, that you have basically different types of filters. Okay, so this most simple filter we got there is using capacitor and a resistor. You can swap those around to create a simple high pass or low pass. You will have to be able to memorize how to draw those, right? They can ask you that. Then you've got the break frequency, which we talked about there, which you can work out by using the equation. We've got, when it comes to filters, which gives us resonance, important point to remember on the curves, your capacitance, reactance, and reactance of the inductor at that particular point there. That's where resonance happens. You've got your bandpass filter, a little bit more complicated, using the inductor and the capacitor. Okay, so we have a look at those. Start off by using basically to work out the frequency response. Okay, on passive filters. Right, first thing about a passive filter, you need to know that there are different types of filters. You've got the low pass, you've got a high pass, and you've also got a band pass filter. But the frequency response will be different on each one of those three. So how do you measure basically the frequency response with those? So just remember, frequency will change. What happens, you basically get a different output voltage on each one. Okay, so that would be a diagram which shows basically a low pass filter. What we've got on these filters is a bandwidth. And that bandwidth, the range of frequencies over which you can get a decent output. Right, the point there we've got is the 70%, 0.7. So how do you actually work out the frequency response of a filter? First thing you have is the AC supply. Okay, so I've drawn a simple high pass filter here. And this is where the output voltage will be. Now with filters, and because they're AC, we'll use a cathode ray oscilloscope over the output. So the cathode ray oscilloscope will actually give us the wave output and measure the voltage. So what we'll do, first of all, we will have to vary the frequency of the supply. Okay, and that is using basically a signal generator, 1 mark for that. So that is something that you can vary the frequency is. Number 2, we will use the cathode ray oscilloscope, and that's going to measure basically the output voltage. And then the third thing that you would do is you would calculate, and you would calculate the gain by dividing the V out divided by the V in. And you do that at certain frequencies. You obviously can't do it at all frequencies, okay? But you would do it at certain frequencies, and then you'll be able to plot that graph of the V out against the frequency. Okay, so that's a 3 marker. You could do that basically frequency response of an op amp as well by doing exactly the same thing, varying the frequencies going in, measuring the output voltage and input, and getting the gain from it. Right, with filters, they like these type of questions where they will give you a characteristic of a filter. Now this one shows a band pass filter, okay, and it is an ideal one, right? An ideal filter. In reality, you wouldn't be able to get a filter which looks like that. Okay, you would get a filter basically which would be sloping at the sides. You would get the 70% points, and that's where your bandwidth is again. Okay, so realize difference between an ideal filter and normal filter. There's your range of frequencies with which this filter works. Now that's going, those lines there basically showing single frequencies that are going in. So no, the only one which will be able to go through there, right? Well, there's the thing at 4 to start with, so don't worry about that one. So that one, the 5, is in that range, so that's going to go through. anything above the 6, that's going to get filtered out. So these frequency response graphs, that should be a straight line to me there. Okay, so same amplitude. Okay, that's what is shown there. That's the only frequency which would come through. Right, it's at kilohertz. Okay, so that is 5K. So what I'm going to do is work out the time period for this particular frequency. Sketch the graph. Okay, so asking us to draw 2 cycles. So time is 1 over frequency. Remember that equation. So we have time. Okay, and that's 0.2 milliseconds. So when it comes to drawing 2 cycles for that, that's basically 2 full waves. It's also asking us to label significant times. I did say sketch. So there's a variety of different options in terms of the size of it that you could actually put in. So there's 1 wave. Okay, and there's the 2nd wave. So labeling significant times. It's 1 wave I got from peak to peak, and that would be 1.2 milliseconds. Okay, so that's a nice little question to do with filters. Just being able to identify what is going into it, what you're going to get out. Okay, and that's a frequency response one, is when you have those lines poking up. Okay. Okay, there's the mark scheme. Okay, I've dropped these in this week. It's basically where you see where the marks are given. Right, what we just looked at there is basically a passive filter. So remember, there are 2 types of filters in electronics. You've got an active and you've got a passive one. Right? Know the difference. Right? Both of them will work on AC. So with a passive filter, passive, think of it, doesn't really do that much as what an active one does. All right, the biggest thing is to do with gain. So with a passive filter, just a capacitor, resistor. When you've got an active one, you're going to have play around with an op amp. Now, an op amp has got the ability to give you gain. Okay, there are 4 types of those active filters that you need to learn. You've got bass boost, bass cut, treble boost. And unfortunately, you're going to have to learn how to draw each one as well. So the biggest thing there is a passive only gives a gain of 1. Okay, so with an active filter, they are very capable of giving you a gain of above 1 or less than 1. Okay, depending on the resistors that you are going to be using. Just as a reminder for you, there's a gain. Okay, this is for an active filter. So there's the bass boost. Okay, so for the passive one, you'd have a gain of 1, flat line every single time, and then it falls off. Okay, go back to the question. There's an ideal bandpass again. Okay, working between a frequency of 2 and 5 kilohertz. Okay, here's your frequency response again. Well, nice little simple question. What are you going to get out? Okay, make sure it's the same amplitude, same position. Okay, that's what I'm looking for with those type of questions. Right, this is a slightly more complicated type of filter. So what we've got in these filters is an inductor, which is that, and a capacitor working together with that resistor to make a bandpass filter. Now, what you get with these bandpass filters, you get a resonance. So at resonance, you basically get the biggest amount of current So what they will do, they're very good at selecting basically a single frequency. It's basically using tuning of radio stations where you aim for one frequency. So with reactances for inductors, equation mentioned at the start, what you've got is XL is 2 pi FL. So reactance means the opposition to the flow of current at certain frequencies. So with the inductor, frequency will increase, XL will increase as well in proportion to each other. Okay, inductance itself measured in henries is constant. So that will always give you a straight line graph. It says sketch, so it doesn't matter about the gradient. Now, if you've got a bandpass filter with a resonant frequency of 0.5 megahertz, and you're asking to work out the reactance of the capacitor, XC is the reactance of a capacitor. Substitute the numbers in. Just watch that mega. Okay, that's 10 to the power of 6. Okay, and we measure multiplying by a capacitor. That's nanofarads, nano minus 9. And that will give you, practice that one on the calculator. If you're watching back on videos, pause. Okay, put it in. It gives you 318.3 ohms. Okay, now the thing is, remember the fact, at resonance, the inductor and the capacitor will have exactly the same resonance. Okay, so amledd cysain i ni siarad beth sy'n ni siarad beth resonance. Okay, mae gyda chi adweithedd cynhwysydd a adweithedd ar anwythydd yn hafal i'w gilydd pan mae'r amledd cysain gyda chi. Pwysig iawn. Felly ar y graff y hunan, ble maen nhw'n croesi, dyna ble mae yr amledd cysain yn digwydd. So resonance always occurs when they're equal to each other. Okay, basically they cancel each other out. Sometimes you're asked to work out the resonant frequency basically from certain equations where you have the inductance and you have the capacitance values given to you. Okay, so look that one up, make sure you know how to use the resonance equation as well. Right, nice little questions these, if you have anything to do with these type of filters. Okay, they will go after basically dynamic resistance, Q factor, bandwidth. So dynamic resistance equation, look it up. What you have in dynamic resistance, that's the one where you turn all the circuit basically into one resistance. So it's nice and easy to work with. The only thing that can be tricky about these, just make sure you're using the correct powers. Got a millihenry, 10 to the minus 3. Okay, and it was a nanofarad capacitor. Okay, so again, people make mistakes on a calculator. It's unbelievable, right? Just practice putting that in. Use your fraction button. Use a 10 to the power button. Okay, on your calculator. Make sure you have your scientific calculator in an exam. Q factor equation, look it up. Straight use. What you're looking for here is your mathematical skills more than anything. Okay, so we've got a frequency there. Came from the question, 5 times 10 to the 6. Okay, using the inductance. Okay, and gives us a Q factor. Give you a quick reminder on the Q factors. Right, that's a small Q factor. So that would have a good selectivity because it's quite a range of frequencies. You've got the high Q factor there. Right, so this one has got very good selectivity. Okay, this one has got low selectivity. You'd have interference maybe on certain radio stations or whatever with that one. Got low selectivity. And you have high sensitivity. Sensitivity is basically if you've got a lot of gain, okay, it will boost it. Right, for your bandwidth, okay, that's the quoted equation, cross multiplication, if you need to be able to work out the bandwidth from there. There's your resonant frequency on top. There's your Q factor, which we just worked out. Okay, so nice little equations to use. Remember, bandwidth measured in hertz. Okay, and that's the max scheme that we got from there. Okay, that's your filters. Obviously, there are a lot more type of questions they can ask you on filters. Basically, yeah, those are your main facts. Know basically the shapes of your graphs for low pass, for high pass, and for your active and passive filters, know the differences between them. What Anders said, as for the active filters, you would have to learn the 4 basically type of filters. Right, we'll move on to switching systems. So when it comes to switching systems, high power switching systems, you've got the basis of all things working around something called a thyristor. So with a thyristor, what you've got is a gate, okay, and what you need is a current coming into there, which basically switches it on with a big enough gate voltage, which switches it on, and when it switches on, basically has 0 resistance. And then what happens, it will stay on. So in a way, it's like a really complicated latch. So it'll latch on with basically 0 resistance, and you can basically use it to switch something on using high power. Right? They're often used instead of relays, because relays have got mechanical switches inside them, get a bit of lag time. Thyristors work really, really quickly. Okay, so we'll look at some of these symbols that you have to know. Obviously, is the thyristor itself. Okay, then what you've got is a triac, which is basically 2 thyristors opposite to each other. So with a triac, you get a gate voltage, which will turn one side on, but then on the opposite side, it'll turn the other one off. So the big thing is, with thyristors, normal one will only work with half a cycle in AC. With triacs, they will work with both cycles. Okay, we look at those. Then you have a diac. Okay, just 2 connections on the diac. Diacs are used to basically have a greater, faster switch on in a circuit. Okay, it's like opening a door with a massive force, so opening it like that, right? And bang, your triac will come on, or your thyristor will come on as well. We look at capacitor commutation, how to turn off basically a thyristor. What you've got then is your diagrams to do with phase change. Okay, when it comes to, sometimes you want to load to sometimes switch on and off, not just on the cycle, on the sections of it. So you're controlling basically heavy machines sometimes with thyristors and with triacs. Here we go. Right, 3 things with a thyristor. They have to have 3 conditions. Right. So first of all, this is your symbol. There's your gate, which is so important. Then be aware that the top part is called the anode, and you have the cathode. Now, in order to make a thyristor come on in the first place, okay, you do need basically certain conditions. So going through the maximum forward current, 20 amps, to get that before it blows up. Holding current needs to keep it on. We've got a minimum gate current, so that we need that in order to turn it on in the first place. Voltage, we need that 2.5 to turn it on as well. Peak reverse voltage is basically what it can handle before it blows up. So if I was looking at the conditions needed to turn a thyristor on, it has to be forward biased. Okay, anode has to be positive compared to the cathode. Right, what we've got there, anode cathode current 1 amp. Right, the minimum gate holding current was 150, so that 1 amp would just hold it if it has been turned on. Okay, anode cathode current 120 milliamps. That isn't enough to hold it, to turn it on. Keep it going. Got a gate current 2 milliamps, not enough to switch it on. Gate current of 10 milliamps was enough, as we only needed 5. Gate voltage of 0.5 would not turn it on. Okay, question says we need 2.5 in the data sheet. So 2.8 would turn it on. So the 3 conditions which make it conduct, basically A, has to be forward biased. F, 10 milliamps more than what was needed. And H, 2.8 volts was more than what the gate voltage had to be. Now, once you turn it on, you've got to have a holding current going down through it. So looking at the options, the other one would be holding current of 1 amp. Would hold it, keep it on. Because the holding current needs 150 milliamps minimum. 1 amp would be fine to keep it going on. So there's a couple of questions there they can ask, like asking in exams. So as I said, what are the conditions? Okay, first of all, you've got to have minimum gate current. You've got to have a gate voltage big enough, and you've got to have an anode which is positive compared to the cathode, right, in order to switch on. And then once it's switched on, it latches as long as you've got that holding current. Brilliant, fantastic. Okay, let's have a quick look at this one. We've got a thyristor. Now, this one is being used to control a heater, but we have something special as well. That switch there will turn the thyristor on, providing the conditions are right. Current comes down, boom, heater is heating up, whatever it's meant to be doing. Now, if the heater is off at the start, S2 is open. Let's look at the voltages. Right, that bit there is our capacitor commutation. Now that's going to be used in a minute to turn basically the thyristor off. It works really, really clever. Right, but at the start, okay, switch hasn't been pressed, S1 or S2 right at the start. So at this point, X is no current. No current, no voltage drop. So that point there would be the same voltage as there. There's no voltage drop, so it's on 12. So part Y, that is open, no current come down here. Both points are on 12 volts. So the capacitor at that point, there's no charge on it at all. So S1 is hopefully momentary press, bang. Press it, that's going to trigger the thyristor, switch it on. Once it switches on, basically it's got no resistance, current is coming down, so that is basically touched to ground, so there's the naught. Are you still at 12 volts? But what's important now to remember to think about, a capacitor has now been charged. Okay, 12 on one side, naught, so it's effectively it's charged. Now, if S1, S2 is momentarily closed, just for an instant in time, this is what happens. Y will have to go down to minus 12 because S2 is closed, that's touched the ground, there's the naught. So what you've got is, difference between there and there was 12 volts. It's got to keep it. It's down to something called the conservation of energy. The capacitor just can't lose that energy. All right. So basically, momentarily pressed, keeps that potential difference of 12 volts. Cleverly, what does this do? That will turn the thyristor off. The reason for that, heater will go off as well. The reason for it is that now, because that X point has gone down to minus 12, that X is where your anode is, that is now negative compared to your cathode. So that thyristor is now in reverse bias. It's not forward biased anymore, right? So that's going to turn it off. So it's a clever way of turning off a thyristor, okay? Now, sometimes they will ask you to explain that in words, right? So the important thing is to say that the thyristor is now not forward biased, okay? The anode is not positive compared to the cathode, so it will turn it off, okay? So what you would then have to do is basically press S1 again in order to open it, start it up again. Okay, we're now playing around with AC with thyristors. Now, with a thyristor here on its own, it's a normal one, that will only work on the positive cycle of AC, right? Because the negative will turn the cathode positive compared to the anode, and so it'll turn it off. Okay, so remember that in a minute. This thing's diac, mentioned it at the start. So basically a sharper turn on of the thyristor. Remember that, it's like opening a door really, really sharply so you can let loads of people. Those two working together, the capacitor and the resistor, will basically create something called phase control. And what that lets us do is it lets us control a little bit of the load, okay, how much of the load comes on and off. So that's the AC input coming in, positive and negative cycle. Right, these are just like graphs they've given us this time. So let's analyze them before I answer the question. So what this is showing, that's the load voltage. So that lamp in this case would be getting a voltage, start at this point, gets the voltage, turns on. Okay, then it goes off on the negative cycle because the thyristor is turned off. Now that graph just reminds me straight away just of basically of a rectifier. All right, so maybe he's got nothing to do with this question, they're throwing that off. Now looking at that, that is phase control. Right, so this is what happens when that resistor there has got a little bit of resistance. There's going to be a difference in phase. Right, this one is showing the voltage of the thyristor. It fires at that point. That's where it switches on. Okay, and this one just shows basically that's a rectifier with no capacitor on it. Okay, so they're testing us here to know, do we recognize the sort of voltage values which go with basically this circuit? All right, so the two which are really, really important, I would say, number one is recognizing that that shows the voltage of a load. Okay, now that and that are opposite to each other if you look at them. Okay, so with this one, that's where the thyristor is off, but it fires are there. And once it fires, there's no voltage drop across it. Negative cycle has turned it off. Okay, and then whenever the thyristor is off is when the load gets the voltage. And so that's important in recognizing those little voltage points. So if we go back now and we look at the answers, so the capacitor was 4. So that's the one which shows basically a little bit of phase difference between them. If the resistance was 0, there would be no phase difference. That's worth noting as well. Right, with a thyristor, that's where voltage follows, when it fires, down it goes. Lamp, was number 2. There's the load. Okay, which is opposite, basically. Okay, we were able to identify the diac. That was the X one. Right, we got 5 statements, and which one's the true one? Go through them. So the important thing there about the diac is that it does improve the rise time. Dismissed everything else. Right, and here we got with a calculation, basically, okay, of phase difference. So we've got 5K, 22 microfarads, and it's the phase shift between the supply voltage and that across the capacitor. So this is definitely one that you need to practice on a calculator, okay? If people haven't practiced putting these numbers in an exam situation, when you're under stress and you're thinking, how can I get that phase angle? You forget about pressing the shift and the tan button, right? And you get lost. So if I'm putting the resistance in, XC is 1 over 2 pi FC, or maybe it's easier sometimes if you work out the value of XC beforehand, putting it in. So if you work that out and then put that number in, that's easier than just doing 1 over 2 pi and all that stuff. And then the important one is pressing the inverse shift, right? So please, please, please have a go practicing that one. So with these numbers, you will end up with a phase difference of 88.4. Okay, and there's the answers in the mark scheme, showing you the marks are given. Right, so I mentioned this at the start. Thyristors are used instead of relays very, very often. Right, just as a reminder, relays, symbol for relay, there's 2 types that you could use. So with a relay, basically, you've got a mechanical switch. So basically, with the output, which might be put on a transistor or a MOSFET, that will then trigger basically the switch to close, and that is linked to a high voltage. Right, you got a symbol for an inductor there, and that is recognized as a relay switch as well. So the biggest thing is that thyristors have a faster switching, okay, than what relays have, because there's no moving parts. Okay, if you ever have a relay, you can hear the click, 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 okay, when it is activated. So that's a good one to remember. Okay, testing procedure for a thyristor. Right, if you put an ohm meter, okay, across a thyristor, and it says anode and the negative lead to the cathode. So this is your thyristor. So if you were to put basically that is a symbol for the ohm meter. Now, if it's not on, that resistance there will be huge. Okay, absolutely huge. But once this thing is on, if it's working okay, that resistance basically should be very, very close to 0 ohms. That's the procedure for testing it, to see if it actually is working. Because thyristors, yeah, okay, because they're used in high power systems, they can burn out sometimes. So in order to answer it, when it is off, you would have a large reading on the ohm meter. Then, when it is switched on, if it's working, that resistance will dramatically decrease. Felly bydd gwrthiant mawr gyda fe pan mae bant I ffwrdd, a wedyn bydd y gwrthiant yn fach pan bydd y thyristor yn gweithio. Okay, so that's the testing of it. Okay, we're going to look at this one now. See what voltage values and stuff are on this one again. So just getting to know basically what the voltage values should be. So in this particular one, it's initially switched off. Close the switch, so it's latched, and then we'll have a look at the voltages. So if it is off, voltage across that point there will be 15. Okay, there's no current coming down. So the voltage basically across the load, there'll be nothing. Switch it on. That point there will go to 0. And when S1 has been switched back off, it's latched. That point there is at 0, 15, lamp is on. Okay, and here's a capacitor commutation. Learn how to draw it. Okay, there's a capacitor, resistor, there's the switch. Let you basically turn it off. Okay, so that is another question that they like asking, is to redraw basically. Add to the diagram in order to show how a capacitor commutation basically works and explain it as well. Okay, and there we go with the mark scheme for you just to have a look at again. Okay, and finally, so what you've got here is a AC supply. Now notice here we've got a triac, okay, which is basically two thyristors working together. Right, so this will work on the positive and it will work on the negative. That's the important thing about it. We've got a trigger pulse coming in. So that trigger is basically going into the gate itself. Okay, and I'm looking at these trigger points. Okay, so that's the voltage being put into the thyristor in order to turn it on. Okay. Now, what we're going to have a look at is this is the voltage across the thyristor. So on the fire, it'll turn on and then it is off. Skip that bit one there because there is no basically voltage, there'll be no current to hold it. So it fires the next one. Okay, that's where it's gone off, fires, off, and fires on this one again. Okay, so that's where it goes on. At that particular point there, as I said, there's basically no voltage. Okay, now that would mean at that point there, you wouldn't have any holding current because there's no voltage there. So at that particular point, bang, your thyristor's gone off. So that's quite a tricky one, right? So it's realize, yeah, at that voltage there, your thyristor is going to go off. So I'd have to wait for the next pulse. So as we said, with the load, it's going to be opposite to your thyristor. So the load will get the voltage once your thyristor is off. Sorry, when it goes on, which means there's no voltage across it. So your voltage across the load will increase at those points. Okay, so as we said, those graphs go hand in hand together. They're always opposite for thyristor and for the load itself. So the important thing with this one is that the negative cycle was being used. Okay, so to summarize, what we've got with thyristors would be, number one, Know your diagrams, learn your symbols for the diac, for the triac, and for the thyristor. Learn your capacitor commutation. Pressing the switch basically makes the thyristor negatively biased. Okay, that will switch it off. When it comes to AC control, know or practice your tan theta in order to work out your phase angle when it comes to thyristors. When it comes to your filters, know the diagrams for your different filters, bandpass, your low pass, your high pass. Know your break frequencies, know that at resonance you have capacitive reactance and inductant reactance that are equal to each other. Okay, so that's the summary basically for filters and for thyristors. Lovely, thanks a lot.